All right, day 20. Today we're going to talk about one of the most intuitive and human-readable models in machine learning, the decision tree.
You've probably heard machine learning models described as black boxes, right? You put data in, an answer comes out, but you have no real idea why it made that choice. Well, what if a model could actually show its work and explain its reasoning just like a simple flowchart? Think about a simple decision you might make. Should I go surfing? First you'd ask, is the forecast good? If yes, then is the wind offshore? If that's also a yes, you go. This simple set of rules is exactly what a decision tree automates. By the end of this explainer, you'll understand how a machine learns to build this logic all on its own. So let's take that simple flowchart idea and give it a bit more structure, turning it into a formal model.
Officially, a decision tree is a supervised learning algorithm, which just means it learns from data that's already been labeled. It's also non-parametric, which sounds complex but just means the model's shape isn't fixed in advance. It grows based on the data it sees. The key idea, though, is that it uses a branching tree-like structure of questions to get to an answer.
The whole process is really just a series of if-else questions. Each answer sends your data down a specific path, deeper into the tree, until it finally lands on a conclusion. It's a very direct route from your input features to a final prediction.
To really get this, we need to know the parts that make up a tree. So let's quickly break down its anatomy.
There are really just 4 terms you need to know. First, the root node. That's the very first question, right at the top. Any question after that is an internal node. It just splits the data further. The path you take based on an answer, like yes or no, is a branch. And when you can't go any further, you've reached a leaf node. That's the endpoint, where the final prediction lives.
Let's walk through a quick example. Imagine we're classifying an animal. We start at the top, at the root node, and the model asks its first question. Does this animal have 3 or more legs? If the answer is yes, we follow one branch. If no, we follow another. Let's say we have a dog with 4 legs, so the answer is yes. We head down that path. That yes branch leads us to an internal node, which asks another, more specific question to narrow things down. For example, does the animal have 3 or more eyes?
Well, our dog only has 2 eyes, so the answer is no. We follow that branch, and it leads us straight to a leaf node. That's the end of the line, and this node gives us our prediction. Dog. See? A few simple questions got us to the right answer.
Okay, that seems logical enough. But the real magic is figuring out how the algorithm learns which questions to ask in the first place, and in what order. So, yeah, how does the algorithm choose the single best question to ask at each and every step?
It uses a divide and conquer strategy, and it's what we call greedy. Now, greedy just means it's not thinking 5 steps ahead. At any given point, it's only focused on one thing, finding the single best question it can ask right now to make the resulting groups as pure as possible.
And what do we mean by pure? Well, a bad split leaves you with groups that are still a messy mix of different classes. We call this high impurity. A good split, on the other hand, creates groups where most of the members belong to the same class. That's low impurity. The goal is always to ask the question that leads to the purest possible groups. To measure this, algorithms use a metric called information gain. You can think of it as a score that tells you how much a question cleans up the data, how much it reduces that impurity. The algorithm simply tests all possible questions and picks the one with the highest information gain. Another common metric is Gini impurity. It's a slightly different way to measure the same idea, essentially the probability of grabbing a random item from a group and getting the label wrong. With Gini, a lower score is better, and you'll often see it used in popular algorithms.
Okay, that's the theory. But where do decision trees actually fit in the real world? Let's talk about the trade-offs.
The number one advantage, by far, is that they're easy to explain. You can literally show the flowchart to a non-technical stakeholder and they'll get it. This is huge in fields like finance or medicine, where you have to justify your model's decisions. They also require very little data prep and work for both classification and regression. But they definitely have downsides. They are notoriously prone to overfitting. They can grow so complex that they just memorize the training data. They can also be unstable. A small change in your data can result in a completely different tree. And that greedy approach means the final tree isn't guaranteed to be the absolute best one possible. To fight that overfitting problem, we use a technique called pruning. It's just like it sounds. You go back after the tree is built and snip off the branches that add complexity but don't really improve performance, helping the model generalize better.
And this is the most important takeaway for modern practice. While a single decision tree might not be the most accurate model on its own, they are the essential building blocks for some of the most powerful algorithms we use today, like random forests and gradient-boosted trees.
So, to put it all in one sentence, a decision tree automates the creation of a human-readable flowchart to make predictions from data.
The key thing to remember is their transparency. That simple flowchart logic makes them one of the most explainable models out there. And this leaves us with a compelling question. If one tree is this intuitive, just how powerful can an entire forest of them be?